And we'll actually we'll think about this same question you did in the warm up today. I don't need you to. I think it's pretty clear just by looking at this where this is discontinuous, given your pre-calculus knowledge. Clearly, at x equals 1, it's discontinuous. But at each place, I want you to stop. If you say, oh, it's discontinuous at x equals 4, I'd like to be able today, after today, I want you to be able to give some reasons why that's true. Not just like, well, I don't know, I have to pick up my pencil as I draw it. Which is basically where we left you in pre-calculus, right? You say it's discontinuous at x equals 1, why? Can we prove it's discontinuous at x equals 2? So just right now, maybe with your groups, I'll give you a minute to just discuss with your groups what's required for continuity. And you do have some new language to talk about here. In particular, the language of limits, maybe. You already, I think, have a sense that these ideas are intimately connected. That, like, think about the trains. Think about the way the graph comes. We need the graph to kind of come together, right? Somehow. But is that all that's required? Think about it. See if you can come up with a definition of continuity that's better than what we said in pre-calc, which is just like, can you draw it without picking up your pencil? Okay, go ahead. Figure something out, and then we'll share out in a second.
I'm listening to the
All right, that's enough. If you don't have it already, then no more time. Okay, who has a definition for me? Give me something at least, some progress towards it. I want to know, how do I know if x is continuous at x equals 3, like I think it is here? How can I know that it's continuous at a particular value? You're so excited, you want to share. Go ahead, Matthew, I haven't heard from recently, and then these guys will chime in if they're excited too. So
our idea was that the limit as x approaches c from either direction, c being any x value, does not equal f of that x value for it to be a discontinuous point.
Okay, I think I like where you're headed with that. Albert, do you want to say it differently, or is it the same thing he said? Or?
I'm pretty. Yeah, I think it's as x approaches c. Okay, so the point, it's discontinuous if it goes to a point, but the actual point is not the point it's going to.
Okay.
Yes.
Yeah.
I'm saying it a different
Peter,
way.
say it your way. You said exactly the same way. You have nothing to add. Josh, say it your way.
We had the same thing, but the one thing we were concerned about is with asymptotes, vertical asymptotes, because there is no limit and there's also no limit.
Okay, so yeah, and you're wondering like, what if you get like D and E and like undefined? Are those equal?
Right.
Yeah, and the answer is no. So you're good. Yeah.
So, the limit has to exist.
Okay, I like that.
There has to be a point X, and they have to be equal.
Yeah, I think that I like hearing all that. Yeah. So why is it sufficient? Why is it not? It is necessary, but it's not completely sufficient to say that the limit exists. Give an example from the picture up here where that would. Yeah. Okay. Yeah, the limit is perfectly good at both of these places. The graph like still kind of comes together, but yeah, we need also for the point to be defined, and not just that, but also defined at that place. So yeah, that's it. We need to check those things. I'll just put them up here quick because you just said it. And this is it. This is right here. Right? So that's the test for continuity, right? Really, it's summed up in this. I think I have it enough. Here it is more formally down here. I think actually this is copy paste from your book right here. Here it is more formally, right? So here it is, the box again appears here. Is it true that the limit as x approaches c of f of x? Is that equal to f of c? That's the question. Now the only other thing that's like such a tight, beautiful definition. I love that. But then we have to come in and say this too. Because on the endpoints of that diagram we were just looking at a second ago, on that function that was defined on that closed interval, we don't want to say that it's discontinuous at either of the endpoints, right? But we all have that intuition. We just want to formalize that intuition somehow. So all we require at the endpoints, because the overall limit at the two endpoints is undefined, isn't it? Because there is only one of the one-sided limits exists and makes sense for us. So all this says down here, I would call this this is the beautiful part. I would call this kind of a footnote to the definition of continuity. We say at an endpoint, we just have to, the value of the function just has to agree with the one-sided limit at that point, right? And that should not be a shock. It's just a shame that we have to come out and say it, but there it is. So at the right, did I say this right? On A, B, yeah. If you're at the left endpoint, A, then the right-hand limit coming to that point needs to agree with the value of the function only. So, good. So see, your math efficiency, you came up with this at least. This isn't strange, but you came up with the interesting part yourselves, but also I think much better than the pencil. Can you draw it without picking up your pencil definition? Everyone okay with all that notation? Another 10 seconds. All right. You good, Rosie? All right.
I finished.
Okay, good. Oh, I forgot. Sorry, there's a smiley face. Yes is the answer. Do you really have to go through all these steps? If someone wants you to verify continuity, the answer is yes. Yes. Certainly, again, let's bring back in, I think I put a slide up there here, almost exactly the same kind of slide. Here, when we're talking about limits, right, we said, when is it safe to just like plug in a value when we're evaluating limits? And a lot of that rests on your prior knowledge from pre-calculus and other courses that you know about things. You know it's always safe to plug things into a polynomial and to evaluate a limit. And it has intimately to do with the continuity. Now we understand why those are true. So certainly we know about continuity. All of these functions, basically every function that we care about in math, for the most part, is continuous on its domain. And this is kind of a critical piece here. I know that you're going to be like, wait, really? rational functions, for example, trig functions are continuous functions? Yeah, actually they are on their domains for every value for which they are defined. It's that every single point for which they're defined obeys the definition that we just talked about, don't they? Now, it's certainly true that, like, the rational function 1 over x is discontinuous on the real line at x equals 0, but is x equals 0 a place where the function is defined? No, but everywhere on its domain, pick any x value for which it's defined, and it's continuous at that value, isn't it? Right? So I know that's a little weird to say. You're like, wait, what about like tangent? Well, actually, yeah, everywhere tangent is defined, it's continuous, right? For every place on its domain is kind of a critical thing to say. And we can say something more powerful too. And I'll just say it kind of informally with this thought bubble, okay? With this beach bubble, rather. All of any combination of these by way of multiplication or by way of division or composition of continuous functions. All the ways you can combine these. If you wanted to do like x squared sine x, continuous. If you wanted to do whatever, tangent x divided by e to the x, continuous. Again, on its domain, wherever it might be defined, it will be continuous. And to prove that is beyond the purview of this course, that's for sure. Okay, so we can come talking about it sometime. If you save it for maybe a real analysis course. Okay, with that in mind, hopefully that conversation is sharply in focus as we answer these questions, because in bold it's key here, right? The bold part is part of the key here. So explain why that first function there is continuous on its domain. Well, because it's like a bunch of continuous functions, right? We've got a composition of a product and a quotient of all of them are continuous functions. So I don't know how we want to say that. It's a combination of them. So it's continuous. We don't have, this is one more reason why we taught you the greatest integer function, because we don't have very many functions. Continuity is such an important thing because it's a property that we can almost always guarantee for all the functions we like. There are very few functions that don't have that property. So that's why the greatest integer function comes in to help us a little bit here. This one isn't continuous on its domain. Can you explain why? Or maybe you can even demonstrate a place where it's not continuous.
Well, for example, at, I think, 3.
Yeah, that's a good question. Where is this not continuous? Where there are jumps. Let's just get that out of the way. This is like the greatest integer function, some transformation of the greatest integer function. Where are the jumps on this thing? Did you find one? It's not 3. Oh, well, no, 3 works, doesn't it?
Well, I was just thinking
Yeah, 3 does work. Anything that makes this an integer. Where else, though? Yeah, also 1/3, right? Or 2/3. Any time this comes out to be an integer here. Why would that happen? Normally the jumps are at the integers. Why is that happening here? What kind of transformation has occurred? Yeah, the 3 takes what kind of action on the graph? Yeah, it's a horizontal shrink by a factor of 1/3, isn't it? So and the -1 interacts with it in an interesting way too, but we could actually go through the work of plotting it, thinking about it more deeply. But yeah, this has jump discontinuities at all those places. And now here I'm saying for all reals, can you just say where tan x isn't continuous? What do we have there? Yeah, at pi over 2 or that number plus pi or any multiple of pi after pi over 2. So, right, those are vertical asymptotes. Now we could even say something more formal though, right? We could actually say why at pi over 2 tangent is discontinuous. Now there's a simple way to do it. You don't even have to evaluate the limit, do you? It's not even defined there, right? So like already I know that the definition of continuity that we gave a second ago will fail. Because implied in this tight definition is that f of c even makes sense, right? So certainly a function has to be defined at a place for it to even be a candidate for the continuity. So that's all you have to say. Okay, switching gears a little bit here. Are we good? Good on continuity for now. At least we'll return to the idea again and again. But this is also connected somewhat to continuity, and this is called the intermediate value theorem. Study it, and then we'll talk. The picture says it all, I guess. There's so much you can do with this, actually, even though it sounds so trivial and so simple. Why is it true that if the temperature in this room this morning was 70 degrees and the temperature at 5 o'clock this evening was 80 degrees, why must it be true that the temperature was at one time during the day 73 degrees? Well, because what has to be the case? I mean, in order for us to make this conclusion, what's true? Yeah.
It has to graduate,
Yeah, and is there any other way for that to happen?
no.
Yeah, and fortunately, most functions that we study in the natural world are continuous functions, right? So we can guarantee that that would be true. Or can you guarantee that at one point in your height, this is kind of an exciting thing for a mathematician to realize, that your height was exactly pi feet tall, right? I mean, I assume that you didn't there was no, that your growth, your height is a continuous function of time, isn't it? Well, you were definitely less than pi height, feet high at one point, and now you're greater than, I think, you're all greater than pi feet tall now. So, yeah, I think if we can assume that's a continuous function, that you were definitely, I don't know, we might have trouble naming when that happened exactly. But there definitely there does exist a time when that happened, that was true. Stamp prices went from, 43 cents, what are they now? 46 cents or something like that. Is it necessarily true that they were 44 cents?
No.
Why?
It's not a
Yeah, or I mean, we certainly can't guarantee that the price was certainly never was 44.5 cents, right? It's not a continuous function, right? So that's the critical thing, right? And we can do other things with this too, besides kind of those fun real world situations. This was especially useful, I think, too, before we had ways of solving numerically these kinds of equations. And we don't even have to do one this complicated. Even if you think of like a cubic, it's very, very easy in math to give someone a problem they can't solve, right? Like, think of a random cubic equation. How can you prove that it has at least one solution? Well, one way to do it would be to prove that, well, you know something about the end behavior maybe, though you might need to prove that. But if you can even demonstrate one place where some cubic is negative, you'll always be able to do that. And another place on the function, when you evaluate the function, gives you something positive. Then how do you know for sure if it's a continuous function? Well, of course it's going to take on the value 0 somewhere. Because it'll achieve every value between whatever the negative y value was and the positive y value. So we don't know where it is, but we can show that it has a solution. So we'll do that here for this function too, and this is a pretty exotic function. See if we can show that this equation has at least one solution on this interval 0 to 1. Yeah, not a function you know how to solve algebraically, do you? Not you might be able to approximate the solutions on your calculator. But. So here's how I might do it. The intermediate value theorem doesn't really talk about two functions. It only talks about one function, doesn't it? So what am I going to do? Yeah, I'm going to move it all to one side. So we definitely will be done if we can establish that this is true, right? For some value in 0 to 1. We'll be done. And then, now we need to think hard about what happens if you plug in 0 and 1 to this thing. What happens if you plug 0 into f, or 1 into f? It does require that you know what e is approximately, doesn't it? So I get, for f of 0, I get approximately 1.7. And for f of 1, I get approximately, well, I haven't said it. Oh yeah, sorry, I put it over there. F of 0 is -1, sorry. And f of 1 is 1.718, right? So this is the conclusion I would write. I would say, okay, this is similar to the reason I was just sharing a second ago. I would say, well, of course f of x has to be 0 then. If this is a continuous function, and it is, it's a combination of continuous functions. So this is what someone would expect you to write, these words. So I hope you see that the intermediate value table is actually kind of fun and powerful. You can make some interesting conclusions from it. Here's the picture, just so you know. Just for fun. Right? Here's f of 0 is -1. Here's f of 1, 1.718. And certainly it's gotta cross the x-axis somewhere, right? This is a picture of f. Here's a picture of the two functions individually, and of course they cross at the same x value, right? It looks like it's about, like, whatever, 0.45 or something, I don't know. But who cares? It doesn't matter what it is. We've proved that there is such a value somewhere. Okay. So let's return to one more idea involving continuity now, if you'll let me. You'll get opportunities to think about the intermediate value theorem some more in homework tonight. Is that okay, anyone? I just did it. 10 seconds is what you get. Good. Yeah. This is kind of, I don't know, kind of cute, I guess. I don't know, it's not. It's kind of strange what we're about to do, but we're gonna patch a hole. Okay, that's what this is called. It's called a continuous extension for a function, and it involves us kind of fixing a hole. And recognize, if you will, first find the discontinuity, the removable discontinuity. I'm already kind of telling you ahead of time that there is one, but go ahead and find it. Resolve this expression by factoring. The picture gives it away a little bit. But this has two discontinuities, right? One of them we can't help. We can't fix this one, sorry. No amount of glue will fix the vertical asymptote on this thing. But yeah, I'd like to think about what this whole should be. Now, when I say like what it should be, that is what's its y value? What should the y value? What does it feel like the y value should be? Well, what dictates what the value kind of should be there? What notion that we've been talking about recently? The limit of the function around that point. We can't ask what the function has as its value here, because I know the answer to that at x equals 2. Sorry, it's here. It's undefined. At x equals 2, it's undefined. That's not helpful. But I can ask what's the limit as x goes to 2 of this thing. And you've already worked it out, I'm sure, here. What is that, x minus plus 3 minus 2. All right, so what do you get? What is it? 5/4? Okay. So in some ways that's like the y value necessary to like plug the hole. So the way we'll write that then is this is called the continuous extension. We're going to call this function g. And the way that we want to write this is this way. Okay? We're going to write it as f, or if you want you could write the whole function again, when x is equal to anything except for 2. We love f. F is a beautiful function, except we'd like to overwrite it, right? We'd like to go in and overwrite one line of the file, you know? At x equals 2, I'd like to define it to be 5/4. Do you see that this is us patching the hole? So this is the way we'd like to write this. And I know that it's exactly equivalent to the function x plus 3 over x plus 2, right? I realize you're thinking that. But I do think this is good for us to like practice writing it this way, thinking of it this way. And there's situations where this is actually going to need to happen, actually. But it definitely emphasizes in the box here, writing it this way, definitely emphasizes what we're doing. Doesn't this look like us patching the hole? Yeah, definitely this looks like us patching a hole. Take that and fill it. There you go. Okay. And now it's the same function as it used to be. It's just now it's continuous. Now it's continuous at that value because the limit, which is 5/4, equals now the value, which is 5/4. So it's continuous there. Yeah.
Would it be feasible if you were to represent like x from -2 or -1 for us to actually patch an asymptote away and make it continuous?
No.
No, never, no way.
I mean, no. I mean, yeah, there is something in when you get into complex analysis, we talk about like the adding infinity as a point, and then like, augmenting that to our set of numbers, and you may think about it another way of doing that, but yeah, the quick answer is no. So, all right, I would love, you might need to be sent, we'll try to get this started at least, but we might need to be sent away with this problem. This is not just like more practice. This is actually a little bit meaty. So go ahead and write this down. And we'll try and patch the hole. I promise there is one, right? But now again, you can kind of cheat a little bit because there's a picture. But even evaluating the limit might be a little tricky. We use this as a vehicle for reviewing things you haven't thought about before. What needs to happen? Has anyone realized? Yeah. It's just like the last one. We just need to factor the numerator into the denominator. So, yeah, I mean, I don't know how comfortable you are factoring the numerator. So, do you remember how to do division? No, you don't. I mean, there's not much you have to test. I mean, you kind of, the only two things that could possibly be a removal discontinuity are 3 and -3, right? And if you trust the picture, maybe you already know what to do, right? If you didn't have the picture, you'd have to maybe test both. But I'm going to just guess from the picture that the removal discontinuity is at x equals 3, right? So knowing that x minus 3 is a factor of this is helpful for me. I already know one of the factors. Can I find the other one that's quadratic? By either doing syntactic division or by doing long division or using like a box method or any kind of division you want, but somehow get the other factor of this. Yeah.
We already have the points here. Or even why do we need to factor it all?
Well, that's good, but we want to plug the hole. We need to find out what the y value is there, don't we?
You don't need to factor it for that. Just to plug it in.
Can you plug in 3 to this? You go first. Plugging in 3 is not super easy there, huh? I think you get something undefined. Alright, so that'll be your take home, right? That's what you said. I think you do need to actually factor it still. So, yeah, see if you remember how to factor that numerator by using division. The long division is kind of the easier. See you guys tomorrow. Bye guys. Homework 3 tonight from the book.